probability. So exploring probability, use probability to make predictions. So there's something called theoretical and there's something called experimental. We're going to learn about both. So let's just review some things. Cards. How many cards are in a standard deck? Not including jokers. Often we use card questions, so that's why we need to go through this. How many? 50 what? There's 52 cards in a deck. We never count jokers, unless for some reason they include them. How many suits are there in a deck, and what are their names? There's 4 suits, right? And their names are, I'm going to go alphabetical. Clubs, diamonds, hearts, and spades. Okay. So a club looks like kind of like this, kind of like a clover. We have our diamonds, hearts. And a spade kind of looks like an upside down heart. Oops, upside down heart. With like a stem, as if it was a leaf. Okay. How many cards are red and how many are black? 26. So there's 26 red, 26 black, half and half. So the red suits are diamonds and hearts. Our black suits are clubs and spades. Right? How many cards are in each suit? Well, is there a 1 card in a deck of cards? Usually it's lowest or highest. What is the first card? Let's call it. Instead of a 1, it's an ace. And then it goes to, is there number 1? No. So there's a 2, 3, 4, 5, 6, 7, 8, 9. Is there a 10? Yes. And then what is it? Jack, queen, king. Okay. So how many cards are there in each suit? How many cards is that? Or think of it this way. If there's 4 suits and there's 52 cards in a deck, there would be 13. No one wants to speak up. Yeah, there's 13 in each suit. Okay. The Jack, Queen, King are what we call face cards because they actually have a face on them. They have a picture of a joker guy, Jack. The Queen has a picture of a queen, a picture of a king. Those are our face cards. Ace is not a face card. So what are the face cards? The face cards are Jack, Queen, King. And how many face cards are there? Well, how many in each suit? First of all, there's 3 in each suit. So how many total face cards would there be if there's 4 suits? 12 face cards in a deck. So a deck is what we call the full deck of cards. Okay, so those are cards. Let's talk about numbers. How many digits are there? Digits. There's 10, right? There's the numbers 0 through 9. 0 through 9. So if you count 0, it actually makes 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 9, not 10. That's 10 digits. How many digits are odd? 5 of them. Yeah, and those are 1, 3, 5, 7, and 9. For a number to be odd, the last digit has to be odd. The other ones don't. Right? How many are even? 5 as well. Is 0 included in that? Yes. Should be review. What digits at the end of a number make it even? So the key here is at the end of a number. So a number is even only if the last digit is even, right? That's how we tell. So we only have to look at the last digit must be 0, 2, 4, 6, or 8. So for example, 132, even though 1 and 3 are odd numbers, As long as the last digit is an even number, 132 is also even. It's divisible by 2. By definition, a number that's even is divisible by 2. And so all that matters is the last digit. What digits at the end of a number make it odd? So that would be the numbers 1, 3, 5, 7, and 9. So for example, 249 is odd. Doesn't matter that the other two digits are even. As long as the last digit is odd, the number is odd. Okay. Letters. How many letters are in the English alphabet? You need to know this. 26. Okay, in mathematics, what are our vowels? A, E, I, O, and U. Is Y a vowel in math class? No. So there are 5 vowels in math class, meaning how many consonants will there be? 21. 25 minus, so 26 minus 5. Okay, so that's just review. So what we're going to do, oh, dice. One more thing is dice. A lot of questions in probability, you'll notice, are going to have to deal with digits, letters, cards, and dice often. So that's why we're just doing a quick review of those. Die. So a standard die. When I say a standard die, what's a standard die? Numbers what through what? 1 through 6. So there's 6 numbers. The numbers are 1, 2, 3, 4, 5, 6. What is the largest sum you can make? So whenever a probability question asks you for the sum of 2 die, it can be really helpful to make a chart. Okay, so you don't have to, but I find it's very helpful for those questions. And you'll see that in your homework, a lot of the questions are dealing with the sum of 2 die. So you have die 1, and you have die number 2. So it also has the numbers 1 through 6. And then we can fill in the sums of the 2 die. So what's the smallest sum you can get? 2. 1 and 1 would give you 2. The smallest sum is going to be 2 with 2 die. What's the largest sum you can get? No, sum. 12. Sum. Yeah, 12. So the largest we can get is 12. So filling in this chart, if I was asking you, for example, what's the probability of getting a sum greater than 7? Okay, that's a type of question you're going to deal with. It's good to have, okay, how many sums are greater than 7? So 1 and 1 is 2, 2 and 1 is 3, 3 and 1 gives you a sum of 4. You'll notice a pattern. 4 and 1, 5, 5 and 1 is 6, 6 and 1 will give you a 7. And then the next row, a 2 and a 1 gives you a sum of 3. 2 and 2 is 4. Do you see the pattern each time? It's really easy to fill in. So 5, 6, 7, 8. The sum here will go 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. And then 7, 8, 9, 10, 11, and 12. So there's all our sums that we can have with 2 die. Okay, so what we're going to do is we're going to do some experimental probability. Okay, so experimental probability is when we actually do an experiment and see what's the probability based on our experiment. So when 3 coins are tossed, what is the probability that exactly 2 results in heads? Now let's talk about probability. When we talk about probability, you can represent it as a decimal, a fraction, or a percent. So let's talk about percent. The range is a percent. It's going to be between what percent and what percent? 0 and 100, okay? So the probability something happens is between 0 and 100%. Always. Okay? So as a decimal, probability always is between 0 and 1 if we change it back to a decimal. So I want you to take a guess. If 3 coins are tossed, what's the probability that exactly 2 results in a head? Make a guess from 0 to 100. What you think the probability is if you have 3 coins that you're going to take in your hand. You know what a head looks, it's a queen, right? So I just got 2 heads. Look at that. Okay? So what do you think the probability of that happening occurs? Make a guess. Take a percentage, write it down. Has to be between 0 and 100. Do you think it's greater than 50? Do you think it's less than 50? Just write some number down. It's a guess. A bad guess would be 110%. It's probably less than 100, and it's probably greater than 0. Okay? So what we're going to do is we're going to get into partners, and we're going to do a bunch of trials. So for example, my first trial, I have 3 coins, so we're going to do one at a time. So I got head, head, tail. So in this case, yes, my trial 1 worked. So then toss, oops, let's just throw them on the ground for fun. Tell me what they are. Tails, tails, heads. Did I get it? No. Okay, so I'm going to give you some coins. Maybe just turn to someone behind you is probably the easiest. Thank you, Owen. Throwing him on the ground probably wasn't really nice. And then I want you to do at least 20 trials. Okay, at least 20 trials. So I'll give you some coins. If you can get with someone just really close to you, that would be preferable. Here we go. Whoever wins. So now, determine the probability of getting exactly 2 heads by dividing the number of trials with exactly 2 heads by the total number of trials. So I, for example, had 1, 2, 3, 4, 5, 6, 7, 8 times in my 20 that I got exactly 2 heads. Okay, so if everyone can actually get that and divide 8 over 20. Or just leave it as 8 over 20. Okay, so for me, what was the lowest? Anyone get, who got a really low number? Yeah, what'd you get? 25%. So 5 out of 20. Okay, anyone had a really high amount? 12 out of 20. Nice. Anyone else get 8? Yeah. Okay, so most of you obviously were between 5 and 12. Obviously, our lowest is 5, highest is 12. So what we're going to do, compare them to your guess, okay? Who guessed a lot higher than what they predicted? Who guessed a lot lower? Really? And who's not telling me? Everyone else. Okay. Or didn't you even make a guess? Is anyone really close to their guess? So I have 40%. You're pretty close. So I have 0.4 or 40%. So what I want you to do now, if we look at the next page, so let's compare our results. Complete the table collecting data from 5 other groups. So you have your results. Let's just actually add yours in here. So you'll be group number 1, your own group. So number of trials with exactly 2 heads, I had 8 out of 20. Okay, so I want you to find 4 other groups. Okay, and write down their results. Okay, then you have how many out of 10? If you did 10 trials, I have 4 out of 10. Sure, if you want. Okay, so you have 7 out of 20. I need somebody else's. What did you guys get? 5 out of 20? 9 out of 20? Somebody had a 5 out of 20. Okay, and Josh, what did you get? 13? 13? You cheated! Okay, let's use it. Okay. You should have 5. Now, why are we getting more data? Well, the more trials we do, does everyone have 5 now? If not, here's some results from people in class. You can steal some of those from the board. Okay, so why are we collecting more data? In fact, if we want to be more accurate, I should get everybody's in class, all the groups. The more trials you do, the closer your experimental probability actually approaches your theoretical probability. Okay, so here, now my total is, So now you're going to have 100 different trials, and then add up all your total. Add up the totals here that you have. 8 plus 7 plus 9 plus 5 plus 13, 42. So what do you get? Figure out what you get. And all right. So did anyone have less than 30% as a total? No. Okay. Did anyone have less than 35%? Okay. Did anyone have between 35 and 40? Okay, what was yours? 37? Okay. Did anyone have greater than 45% in their sum? What did you have? 49? Ooh, that's really high. Yeah? 46? You got 51. Wow. So we're getting, right now, we're getting a range between 37 and 51, right? The more trials we do, the more accurate it's going to be, and our range of our as a class will be smaller and smaller. Yeah? Yeah? So these are the total number out of the people, all these groups. This is how many heads, 2 heads and tails, out of the total number of trials that we all did combined. Yeah? Okay, so this total was 42 for me. This total here was 100. So 42 out of 100 trials with the 5 groups I've talked to, including my own, me including. Okay, so as a class, let's try and draw a tree diagram to get the theoretical probability. How are we going to get that? Well, let's see how many times it's possible to occur out of the total number of outcomes that are available. So the first coin can either be a what or a what? Head or tail. Okay, so either try and give yourself some room, right? Because we're doing a tree diagram. Now, when you roll the second coin, it can then also be a head or a tail. And the third coin, we roll again. Or roll. I don't know why I said toss. You toss a coin. You don't roll a coin. Silly. Head, tail, head, tail, head, tail, head, tail. So our outcomes that are possible here are, we go up the ladder, right? We can get head, head, head. 3 heads. We can have head, head, tail. So you see how I'm changing them into the different outcomes? You can have head, tail, head. So finish this off. All the different outcomes. Head, tail, tail. So how many total outcomes do we have possible? How many did you count? How many is that? 8, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 different. And which one of these? So let's circle the ones that actually have exactly 2 heads. So circle all the ones that have exactly 2 heads. 1, 2, 3. You see any more? That's it, right? Exactly. So calculate the theoretical. The theoretical probability is the number of favorable outcomes over the total number of outcomes. So favorable, there's 3, right? There's 3 different outcomes that are available out of a total number of 8. What does 3 over 8 equal? Oops. guessing it's pretty close to that 40% mark, 0.38%. Well, let's say 0.375 or 37.5%. So that's the theoretical probability that it occurred. Did you notice that the more trials we did, the closer we got to that 38%? And if we kept doing more and more, it should get closer and closer and closer to that 38%. If we did infinite amount of trials, we should get 37.5% of the time, we'll have exactly 2 heads. So the more trials we do, the more closer our experimental probability gets to our theoretical probability. Okay, what do you think we're going to be doing in this class? Experimental more or theoretical? Probably theoretical, yeah. Unless you're at an exam and you're tossing coins 20 times. That would be fun. I guess that could be a fun test question. Okay, so that was fun. Key ideas here then. So experimental probability. So N of A is the number of times the event occurs. N of T is the total number of trials, right? And that's what we just did, right? So how many times did it occur out of the total number of trials gives us our experimental probability. We are mostly going to cover theoretical probability. So theoretical probability, what is NA and what is NS? Well, NA is the number of favorable outcomes. So you'll hear that word a lot, number of favorable. And S, the reason why they do S is because it's a sample space. So we've talked about sample spaces. You hear them a lot when if you covered, remember, statistics last year. We talked about sample spaces as well. So this is basically the total number of outcomes over the total number of possible outcomes in our sample space or in our problem. Okay. So favorable over total is essentially the formula. So the probability of event occurring is the number favorable over the total possible. What makes a game fair? Well, it's fair if all players have an equal chance of winning. Okay, so all players are equally likely to win. And we'll look at some examples, whether something is fair or not. Also, things to remember when we're dealing with theoretical probability, you can either write it as a fraction. So we had 3/8, for example. We can write our probability as a decimal, 0.375, or as a percent. Times it by 100, 37.5%. So probability could be any of those ways. We know that you can't, like you'll hear people say, I'm 110% sure, right? In probability, if something is impossible, there's a 0% chance of it happening. If it's certain, it's a 100% chance. We can't have more than 1. So probabilities are between 0 and 1. If it was a decimal, as a percent, between 0 and 100%. Okay, turn the page. You're almost done. Let's actually look at some problems. So what is the theoretical probability of getting a 5 when tossing a 6-sided dice? So the probability of rolling a 5 is how many times does a 5 occur, the favorable, over the total, okay? So favorable over total. So probability equals favorable over total. So how many times does a 5 occur on a die? Once. So once is the number favorable. There's only one time it occurs out of a total of how many different digits on a die? Possible of getting 6. So our probability of rolling a die is 1 out of 6. Okay. What is the theoretical probability of getting an even number on a die? So what are the even numbers? Even numbers are on a dice or die 2, 4, 6. So how many? It's really the number of favorable, right? So I should say number of favorable over the total number. So how many times Do we have an even number? We have it 3 times out of a total of 6. Or we always reduce our fractions. If you have a probability, always reduce it. So 1/2 or 50% or 0.5, you could write it as 2. Okay, what is the theoretical probability of getting a number greater than 2? When they say greater than 2, does it include 2? No. If they wanted to include 2, they'd say greater than or equal to. Okay, so if it says greater than 2, we're talking about the numbers 3, 4, 5, and 6. So the probability of greater than 2 is equal to, how many times will it occur? 4 times. There's 4 numbers greater than 2 out of a total number of how many numbers on the die? 6. What does that reduce to? 2 over 3. Okay. And the last thing we want to look at is whether something is fair or not. So in order for something to be fair, we should have an equal chance of winning. One person can't have an advantage over the other. So consider each game below. Is it fair? If it's not fair, explain who has the advantage and why. So Matt and Pat each toss a coin. If the coin lands as both heads or both tails, then Mart wins. If it's both heads, both tails. If the coin lands as a head and a tail, then Pat wins. So to figure out if it's fair, let's write down all the possible outcomes. So we can do, they're each tossing a coin, right? So we have head, tail, so Matt's coin. I'm going to do a tree diagram. And then the second coin, hat, head, tail, head, tail. So our possible outcomes are 2 heads, head, tail, tail, head. So the first is head, the second is tail, or the first is tail, the second is head, and then tail, tail. So would this be a fair game? Well, if they're both heads, we said Mart wins. And if one tail, one head, then Pat wins. So would this be a fair game? Yes, this is because they each have the same likelihood of winning, 2 and 2. This is a fair game. Sounds thrilling. It's a game you could play. You know? Probably not. Trina, Lena, and Gina each toss a coin. If all 3 coins land as heads, Trina wins. If all 3 coins land as tails, not rails, sorry, then Lena wins. Otherwise, Gina wins. Okay, so let's do all our possible. We did these ones before. We did this chart before on the previous page. Remember, this is the exact same situation we were just dealing with. So we had tails, 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 heads, tails, heads, tails, tails, heads, heads. And then we had heads, tails, tails, heads, tails, heads. And heads, heads, tails, heads, heads, heads. Okay, so those were all, we already did those. We already made a tree for this, so we're not going to make another tree. So there should be an 8. Remember, we got 8 different possibilities. So if all 3 are heads, Trina wins. So this would be Trina. If all 3 are tails, oops, this is Trina. This is be Lena, right? I don't know, because it's fun. This is Lena, all 3 tails. Okay, and the rest is Gina. So is this a fair game? Gina, Gina, Gina would win. Gina would win. I would want to be Gina, and I would want to, maybe bet some money on this if this is the case. So this is not fair. Gina has well, there's 6 out of 8 chance of winning. It's It's not equally split. They're not all, it's not a fair game. Gina, taking advantage of Lena and Trina. Cruel. Okay, last one. Anne and Dan each roll a standard die. If the sum of the two die is greater than 7, Anne wins. If the sum is less than 7, Dan wins. If the sum is 7, they tie. This is actually a game for gambling, right? Over under. You ever walk the expos? What's it called? It's capital X. No, it's K-Days now again. They change the name every year, feels like. There's a game that people bet. It's called over under. To be over 18 because it's gambling. And this is a common game. So you can either bet on under 7, over 7, or exactly 7. Right? So let's write out our sums, okay? Except for they have like a thing. Yeah, but anyways. But essentially, this is same kind of idea. One of those turning things, I don't know. So let's write out all our sums. So how many total outcomes are there? How many total sums? 36. And we're going to use our knowledge from last unit in the future, right? We could also get our total number of sums. We have our first die, die 1, and die 2. So die 1, we have 6 options, times die 2, we have 6 options, right? That's fundamental counting principle. That's a 36. 6 times 6. We're going to have 36 different outcomes. All right? So that's where our fundamental counting principle is going to come in. And we're going to do situations. What's the probability of the twins standing together when there's 4 different people, including the twins, right? Those are the type of situations. So we're going to have to use our knowledge from permutations and combinations. So here, if we look at this, where does Dan win? Dan wins if the sum is less than 7. Does that include 7? No. So how many times is that? It's all of this. Oops. It's all of this. We circle the inside of this. How many times would that be? How many numbers are less than 7? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15 out of 36. 16? Okay. And is it greater than 7? So greater than 7 is and, so that doesn't include 7. That's all this area here. Is that the same number? Is that also 15 of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So and is 15 out of 36, and there's 6 out of 36 sevens. But if the sum is 7, they tie. So is this a fair game then? Yes, it is a fair game. Because they're both odds of winning is 15 out of 36. Everything else is a tie. So game is fair. Okay. Your homework, it's really short. It is. It's 1 page. 3 questions. So what page is it? Somebody help me find it. Your workbook? So 3.1, page. What page is it on? 55. All. Okay, so it's 3 questions. That's all it is. And we've lots of time. We might even start 3.2 if everyone finishes. No? Okay, we'll see. Yeah, it's short. It's coming to a close.